We'll start with Yash Deshmukh, who will speak on homotopy rigidity of nearby Lagrangian fibers.
Thank you. Thank you for the opportunity to speak, and thanks everyone for coming. So as the title says, I want to talk about the rigidity phenomena in symplectic geometry. So symplectic geometry has already shown up in a couple of talks last week. And in Fezzi's talk, we even saw an example of rigidity coming from phenomena arising from embeddings of symplectic manifolds into other symplectic manifolds. So in this talk, I want to talk about another kind of rigidity that shows up, those coming from looking at embeddings of Lagrangian submanifolds. So the actual problem that I would like to get to, which I'm thinking about, is a lesser known cousin of a more well-known problem called the nearby Lagrangian conjecture. So I will spend maybe more than half of my talk trying to get through this nearby Lagrangian and why one could think of the conjecture being a reasonable statement. So let's start with some background. So some of this was already covered in the talks last week, but anyway, I'll go over it, no harm in reminding. So remember, we are going to talk about symplectic topology, and symplectic topology is the study of symplectic manifolds. These are smooth, even dimensional manifolds which are equipped with a symplectic form. And what is a symplectic form? A symplectic form is a two-form which has the following properties. First of all, it needs to be non-degenerate, which means that the top power of the symplectic form is a volume form on your smooth manifold. So in particular, the symplectic manifolds are going to be oriented. You see this. You see that from this condition. And the second condition, which is maybe somewhat more mysterious, is this closeness condition. So we define that the symplectic two, the non-degenerate two form be in addition closed. So one way to think about the closeness condition is to think of it as some sort of integrability condition, which allows us to choose local coordinates so that locally your symplectic manifold will always look like a standard symplectic structure on Euclidean space of 2 in dimension. So it's not that hard to actually verify that if you have a non-degenerate form, it will be closed if and only if everywhere you can make choices of local coordinates so that the form looks like the standard symplectic form. So this is maybe one way that you would want to think about it. And in particular, it points to this phenomena that came up also in Chris's talk, that locally the only local invariant of a symplectic manifold is its dimension. Any two symplectic manifolds are going to be locally symplectomorphic. So it is indeed an interesting question to figure out whether there are any global invariants of symplectic manifolds. So just to get a hang of what symplectic manifolds is, I mentioned here a couple of examples that might be good to keep in mind as we progress, but the most interesting example is going to be one after this. So maybe these examples are those which you are more familiar with. So the first one is any surface, by which I mean two-dimensional real smooth manifold equipped with an area form. So the area form gives you a symplectic form, and it's automatically closed because it's a top form on a two-dimensional manifold. Another thing that might be familiar with people from algebraic geometry, complex geometry, is to think of smooth projective varieties, or in general, smooth quasi-projective varieties. So these embed inside projective spaces, and projective spaces themselves carry a Kähler structure. In particular, they carry the Fubini-Studi form, which is going to restrict to a Kähler form on these subvarieties, and the Kähler form gives you a symplectic structure on the subvarieties. So one way to think about symplectic manifolds would be to think about complex varieties, but they are in some sense more topological. Okay, so this is the example that's going to be the most relevant for this talk, which is cotangent bundles of smooth manifolds. So you start with any smooth manifold Q, For simplicity, I'm going to keep assuming that it's compact, but there's no reason to do it. But anyway, it will make things simpler. So you start with a closed, smooth manifold, and you take its cotangent bundle. We see that the cotangent bundle carries a canonical symplectic form, and the symplectic form is given by this formula that I mentioned here. So what the symplectic form is supposed to do is it takes a vector in the tangent space of the cotangent space, and the way so the symplectic form is itself defined as a differential of another one form, and the one form has the following definition. Namely, if you give me a vector at a point in the cotangent bundle, the way this one form acts on this vector is it projects it down to the base and then acts at the point at which you had the vectors. So alpha comma v is a point in the cotangent bundle. So alpha is in particular as a covector, which is going to act on a tangent vector in the tangent space of Q. And the tangent vector we choose is the push forward of the vector in the cotangent bundle. So maybe the expression's a bit more complicated, but the point is just to explain that it has a canonical form. In local coordinates, it's always going to look like this formula here. And maybe it doesn't hurt to always think of T star S1 if you are seeing it for the first time. So Q is the coordinate along the zero section, P is the coordinate along the fiber, and the canonical forms are always going to have this local formula. Okay, so this is the example that we are going to be concerned with. And then last week also we saw that symplectic topology is supposed to be some sort of geometric framework for doing Hamiltonian dynamics. So in particular, there are particular flows on symplectic manifolds that will be of special importance for us, and these are so-called Hamiltonian flows. And one geometric way to characterize Hamiltonian flows is the following property, that whenever you pick a loop and you let the loop flow along the Hamiltonian flow, the area that's swept out by the loop is zero. So the area is the area computed with respect to the symplectic form. Remember, symplectic form is a two form, so it allows you to integrate on this two-dimensional thing swept by the loop. Okay, and it's not difficult, again, to check that this actually coincides with the definition of Hamiltonian flows we saw last week, namely in local coordinates. You can choose a time-dependent Hamiltonian so that the equation of your flows look like the Hamilton's equation of motions. Okay, so this is a geometric, this is maybe a slightly more geometric way to think about the Hamiltonian flows. So the rigidity phenomena, as I mentioned, that I want to discuss have to do with certain kind of submanifolds called Lagrangian submanifolds. And here is a quote from Alan Weinstein, who's one of the founding members of the field, which says that everything is a Lagrangian. So from this, you might be able to guess how obsessed symplectic geometers are with these kind of submanifolds. Of course, if you want to understand what the definition is, it doesn't help. So here's the definition. So a Lagrangian submanifold inside a symplectic manifold is going to be a half-dimensional manifold, such that the symplectic form vanishes on the submanifold. So here are some examples of Lagrangians. So first example is graphs of symplectomorphisms inside products. And this in particular gives you a way of transferring questions about symplectomorphisms of a symplectic manifold into itself into intersections of Lagrangians with the diagonal. Then from the two examples we saw before, these are the Lagrangians in those, these are Lagrangians inside those examples. So the first one is any curve inside a surface is always going to be a Lagrangian because symplectic forms are two form, and if you restrict it to a curve, it's going to vanish automatically. Other example is if you have a smooth projective variety, you could look at its real loci, and it gives a Lagrangian submanifold. And then again, these are the examples that are going to play the most significant role in what's going to follow. So cotangent fibers and zero sections. So you can check that the symplectic form indeed vanishes on these things. So again, as I said, many things such as fixed points of symplectomorphism, etc., can be transferred into questions about Lagrangians and their intersections with each other. So you would like to understand what are all Lagrangians inside our symplectic manifolds. So the overarching goal is to just understand all Lagrangian submanifolds inside our symplectic manifolds. And again, we always work with these special types of isotopies, namely Hamiltonian isotopies. So we want to look at all the Lagrangian submanifolds up to these Hamiltonian isotopies. And of course, as you can imagine, this is impossibly hard questions. So we would like to think about ways of simplifying this question. So one of the things that's nice about Lagrangians is that all Lagrangians always have a standard tubular neighborhood. Namely, it's the Weinstein neighborhood theorem, which says that every Lagrangian Q inside the symplectic manifold is always going to have a tubular neighborhood, which is symplectomorphic to the cotangent bundle of Q with the standard symplectic structure that I explained. So whenever you see a Lagrangian, you have a pretty good handle on how the neighborhood of the Lagrangian looks inside the symplectic manifold. So you could try to maybe be more humble and formulate a goal that's less ambitious and say that I'm going to figure out what are all the Lagrangian submanifolds inside the cotangent bundle. So clearly, if I give you a Lagrangian and you take another Lagrangian that's C0 close to the given Lagrangian, you can treat it as lying inside the cotangent bundle. But sometimes you can do more. If the Lagrangian is C1 close to the given Lagrangian, you can actually interpret it as the section of the normal bundle of Q. In particular, you can think of it as, since the normal bundle itself coincides with the cotangent bundle, you can think of it as a graph of one form, and you can check that the Lagrangian condition translates to saying that the form is actually closed. And sometimes you can say even more. If you have a Lagrangian that's Hamiltonian isotopic to the given Lagrangian and C1 close to it, then you can look at the one form on the zero section, one form on Q whose graph this Lagrangian is, and since the condition of being Hamiltonian isotopic translates to it being an exact graph of an exact form. So if I give you a Lagrangian, these are ways of constructing other Lagrangians in tubular neighborhood of those Lagrangians. And so you can ask whether there are any other Lagrangians at all inside this tubular neighborhood. And here's where the conjecture comes in. So this is a very well-known conjecture called the Arnold's nearby Lagrangian conjecture, which says that up to this condition, which I will say what it is, any Lagrangian is Hamiltonian isotopic to the zero section in the cotangent bundle. Any closed exact Lagrangian is Hamiltonian isotopic to the zero section in the tubular neighborhood. So what is this exactness condition? The exactness condition says that if you take the canonical one form in the cotangent bundle, it restricts to an exact form on the Lagrangian. So remember, from this description, you can see that all the Lagrangians which are graphs of exact one forms are exact. And it's also not difficult to verify that anything which is Hamiltonian isotopic to the zero section is going to be also exact. So the Arnold's conjecture basically saying that it's as good as it gets, namely if you give any closed exact Lagrangian, it's going to be
1 minute.
Hamiltonian isotopic to the zero section. So here are some consequences of the nearby Lagrangian conjecture. It says that anything which is closed exact Lagrangian in the cotangent bundle is diffeomorphic to the zero section. You can reinterpret it again as saying that if two cotangent bundles are symplectomorphic, then the underlying manifolds have to be diffeomorphic. So in some sense, you are able to translate the question about diffeomorphism type of the manifold into symplectomorphism type of the cotangent bundle. So there are some known cases and topological approximations of this conjecture that are known, but the conjecture remains wide open in the generality that it's stated. So another interesting question related to cotangent bundle is, instead of looking at the zero section, you look at the other source of Lagrangians, which is the fibers inside cotangent bundle, and ask if you have a Lagrangian that coincides with the fiber outside a complex set. Can I always say that it can be made Hamiltonian isotopic to the fiber? And again, there are some very few known cases, mainly these two cases in 4-dimension, but in general, it's unknown. So we are trying to think about what happens to a homotopical approximation of this question. That's my time. Thanks.
The time for a short question.
And what happens? Oh, yeah. Could you just repeat the definition of exact?
So the cotangent bundle carries canonical one form, this form that I
that
explained
form.
initially. That form needs to restrict to an exact form on your Lagrangian.
Other questions?
Yes.
I'd like to thank the speaker.